In this video, we're talking about inverse Laplace transforms, also called reverse Laplace transforms. And in this particular problem, we've been given the function capital F of s is equal to s plus 3 divided by s squared plus 4s plus 13. And we have this function. We've been asked to use an inverse Laplace transform to change it into a function for f of t. So normally when we have a Laplace transform problem, we start with a function f in terms of t. We start with f of t, and we're using the Laplace transform to get to f of s. And we call this an inverse or reverse Laplace transform because we're just going to be going backwards. We're going to be starting with capital F of s, moving to f of t. So as a reminder here, we've got a couple formulas we're going to be using. And remember that normally when we would start with f of t, we'd be looking here at the left-hand side of the formula at the value in terms of t, and we'd be looking to perform the Laplace transform to change it to the right-hand side, a function in terms of s. And of course, we're going to be going backwards. We're going to be looking at the expression in terms of s and trying to change it back into a value in terms of t. So what you want to do with a problem like this one is you want to, if you can, identify some formulas from your table of Laplace transforms that are similar to the expression or the function you've been given. And in this case, we can see that we have these two values here. We have s minus a divided by s minus a quantity squared plus b squared, and this value b divided by s minus a quantity squared plus b squared. Both of those look pretty similar to the value that we've been given. But notice that the denominators of both of these fractions are the sum of two squares. So what we want to do is see if we can try to transform our denominator so that it is also the sum of two squares. And the way that we're going to do that is by completing the square. So remember when we complete the square of a quadratic function like this one, s squared plus 4s plus 13, what we want to do is first make sure that the coefficient on the s squared term is 1, and in fact it is, so we can go on to the next step, which is to take the coefficient here on the first degree term, so in this case that's positive 4. We want to take that value and we want to divide it by 2. The result is 2, and then we want to take that result and square it, and the result of that is 4. This value then right here is the value we want to add into our quadratic expression in order to complete the square. So what we want to do then is change that denominator. We'll just work with that denominator directly. We want to add in this value right here, 4. So we'll say s squared plus 4s. Here's where we want to add in 4. But we can't just add in 4 because that'll change the value of the denominator. So when we add 4, we also have to subtract 4, and then we keep our plus 13. So the value we want to focus in on then is this s squared plus 4s plus 4 because we added 4 to complete the square with these first two terms. Now this s squared plus 4s plus 4, if we factor it, what we get is s plus 2 quantity squared. Then we want to simplify our negative 4 and plus 13 into plus 9. So what we're doing is we're just changing the way that our denominator looks, but we haven't actually changed the value of it. Remember that the denominators of these two formulas we're going to try to use are both the sum of squares. We have this s minus a quantity squared value, but then we have this b squared value. So we're going to change this 9. Instead of calling it 9, we're going to call it 3 squared. So we're going to say that this is going to be plus 3 squared. This part here, the s plus 2 quantity squared, notice that the denominators of both of these formulas are an s minus a, not an s plus a. So what we want to do is change this to an s minus a negative 2, because if we say s minus negative 2, it's the same as s plus 2. These negative signs cancel to become a positive, but now we have this minus sign here, just like in the formulas. So we're going to say s minus a negative 2 quantity squared plus a 3 squared, and that's going to be our new denominator. So then let's go ahead and write out our function. We'll say capital F of s is equal to, here we're going to say s plus 3 divided by the new denominator we just found, s minus a negative 2 quantity squared plus 3 squared. At this point, we're starting to hone in on the formula that we should be using. Notice that we have this s minus a quantity squared here, where a is negative 2. So in this fraction, we've identified this value right here as a equals negative 2. We also identified this value right here as b equals 3. So if we compare those to our formulas here, the denominators were all set up for either denominator because both denominators are the same. So the difference between these two formulas is really the numerator. In this formula, we have s minus a. In this formula, we just have the constant b. In our numerator here, we have this s plus 3, so we're going to have to use this first formula that includes s in the numerator. So what we want to do is change our numerator to s minus a instead of s plus 3. So keep in mind here that in the formula, we have a and we have a. We already said in our case that a was equal to -2. So what we're going to need is we're going to need s minus a -2 in our numerator. So if we look at the numerator here, s plus 3, if we say s minus a -2, it's like we're adding 2 because these negative signs cancel and we get an s plus 2. So what we want to do is subtract out a 2 so that we don't change the value, and then we have a plus 3. And we know that we haven't changed the numerator because here we have s minus a negative, which is a plus, so s plus 2 minus 2. The plus 2 and the minus 2 cancel, so this is really just s plus 3, our original numerator. So we haven't changed it, but now we can focus in on this s minus a -2 and call it s minus a, because we said a was -2, and so we really have s minus a, which is that form we need in the numerator. So our numerator then becomes s minus a -2. We have a -2 and a plus 3, which is going to give us a plus 1. So we'll focus in on this, and then our denominator is going to be s minus a -2 quantity squared plus 3 squared. And so we have f of s is equal to. So now what we want to recognize is that if we can get rid of this positive 1 right here, then this entire fraction will match the form exactly of the right-hand side of this first formula. So how do we get rid of the positive 1? Well, all we have to know is that when we have two terms in the numerator and they're added together or subtracted from one another, we can just split them apart into two separate fractions. So what we get is capital F of s is equal to, we'll just take the s minus -2 divided by the numerator of s minus a -2 quantity squared plus 3 squared. Then we'll pull out the positive 1 and we'll say plus 1 divided by the same denominator, s minus -2 quantity squared plus 3 squared. Now that we've split apart the fractions, the first fraction has the exact same form as this formula for e to the at cosine of bt. And we just recognize that we have our value here of a, -2, a equals -2. So we have s minus a, and we have s minus a. And then we have our value for b here in our denominator of b equals 3. So what we can say is that if we want to do the reverse Laplace transform or the inverse Laplace transform, then we can go ahead and say that f of t is going to be equal to, because f of s becomes f of t, so f of t is equal to, and we just work our way from right to left in the formula. So we're going to have e to the at, so a again comes from a on the right-hand side, which we already know is -2. So we're going to have e to the -2t times cosine of bt, and of course b comes from the value of b on the right-hand side, which we've already said is 3. So what we're going to end up with is cosine of 3t. So we've transformed then this first fraction. This part's done. Now we need to transform our second fraction. And what we notice here is that the form of this fraction matches exactly the right-hand side of this formula here for sine of bt. So again, we have our same value for a of -2, which matches this value a here. So we have s minus a quantity squared. We also have the same value for b, where b is equal to 3. The only thing we don't have is b in the numerator. In our numerator, we have 1, and we need it to be 3 because we've already said b is 3 based on the denominator. So how do we get this numerator to be equal to 3? Well, what we want to do is we want to multiply this 1 by 3 over 3. And you're going to follow the same process every time when you need to get the numerator to match the denominator, when you need to get this numerator to be b when you've been given b from the denominator. So we're going to multiply by 3 over 3 because 3 over 3 is 1, and multiplying by 1 doesn't actually change the value at all. So we're not changing the value, but look what this is going to allow us to do. So we multiply by 3 over 3. We could then change this, since this is 1 times 3 over 3, we could pull out the 3 from the denominator, and we could call this whole numerator 1/3 times 3, right? Because we would have 1/3 times 3 is 3 over 3. That's the exact same numerator we have here. So if we pull out the 3 from the denominator and we call it 1/3 times 3, then what we can do is we can factor out this 1/3. We can bring this down in front of the fraction, leaving us with only 3 in the numerator, such that we have b in our numerator. So what we want to say is we have this 1/3 down in front. So now doing our inverse Laplace transform, we'll say plus 1/3, and then we're going to work from right to left in our formula here. We already know b is 3 and a is -2, so we just get that 1/3, which we have to make sure we include, times e to the at, so e to the -2t, times sine of bt, where b is 3, so sine of 3t. And then this function, f of t, is then the inverse Laplace transform of the original function, capital F of s, or we could also call it the reverse Laplace transform, which we found by matching our original function for capital F of s with formulas from our table of Laplace transforms.